Hi, I am Daksh Arora, roll number 2201010033, and this is my DA623 assignment demonstration on polynomial regression, specifically a comparison between the Vandermonde basis and Legendre basis. In this video, I'll walk you through a Python notebook where I show you step by step why the choice of polynomial basis matters a lot for numerical stability, even though both bases fit exactly the same curves. The key question we are answering is, if two bases produce the same result, why should we prefer basically one over the other, right? Let me start with the core idea. In polynomial regression, we want to fit a polynomial of degree k to some data. We write it as a linear combination of basis function. The standard choice is monomial basis, which is 1 t, t square, t cube, and so on. This leads to Vandermonde design matrix. The alternative is the Legendre basis, a family of orthogonal polynomials defined on -1 to +1. This leads to the Legendre design matrix. As you can see in the comparison table here, both give the same fit quality. The difference shows up entirely in numerical properties like correlation, condition number, and stability. Let's now open the notebook. The first plot, so these are basically the basic functions of Legendre polynomial scaling from -1 to 1, and least square fit function, something like this. So basically, now the first plot we are having, here we are comparing the shapes of both sets of basis functions. On the left, the monomial basis is there. Notice how as the degree increases, the curve all start to pile up and look very similar near the edges. This is the first sign of trouble. If two columns of your design matrix look alike, they carry redundant information. On the right, we have Legendre polynomials. Each one of them has a clearly distinct oscillating pattern basically. This diversity is what makes the Legendre basis numerically well behaved. Now let's move on to the heat maps for these polynomials. The next plot makes the column similarity problem more concrete. We compute the Pearson correlation matrix between the columns of design matrices for degree up to 15. Ignore this 0 degree thing. The Vandermonde heat map is almost entirely in yellow color, meaning almost every column is highly correlated with every other column. This can be thought simply as well, because we can directly say that t and t square are very much related, they are not unrelated, right? The average of diagonal correlation is basically very close to 1, it is 0.79. This is very bad. The Legendre heat map is almost entirely white completely. The off diagonal entries basically are nearly 0, and the columns are basically nearly orthogonal, we can say. So as we can see, the correlation is 0.0334, which is very less. This directly explains why Vandermonde creates a nearly singular system. Okay, now we want to quantify this with the condition number kappa of x transpose x. Remember, in the polynomial regression, we solve the normal equations x transpose x times a equals x transpose y, right? The condition number tells us how sensitive the solution is to small errors in the data. A condition number of 10 to the 12 or larger means we have essentially lost all numerical precision. Look at this log scale plot over here. Uh, the Vandermonde condition number grows exponentially with degree like It crosses 10 to the power 12 by around degree 8, and we can say it reaches 10 to the power 18 at degree 19. The Legendre condition number grows much slowly and stays moderate throughout. The bar chart on the right shows this is not a small difference at degree 15. Uh, at degree 15, basically, the Wandermond is tens of millions times worse, right? Now, let me now show what this actually means in practice. Uh, Let us add a tiny perturbation, epsilon equals to 0.02 to the data, and then we refit the polynomial and measure how much the coefficients change. I repeat this 50 times to get a distribution, and the box plot tells us the complete story. At degree 15, the Wandermond coefficient shift by an average of thousands of units in norm. Legendre coefficients barely move. That is what I'm showing in this slide. That it is roughly 1,000 times more unstable from a noise level that is smaller than a typical measurement error in real life. This is what the tutorial calls coefficient instability. The monomial basis is fragile, is very fragile coordinate system, we can say. And this is very obvious from the plot itself. Now, here is the most important insight. I fit both bases to the same noisy sine data with degree 10, and the left panel that we are having shows the fitted curves. They almost look identical, almost basically no difference we can see. You can barely distinguish them, but look at the right panel. The magnitude of Wandermond coefficient are thousands of times larger than Legendre coefficients. Same polynomial space, same curve, completely different internal coordinates, and Wandermond coordinates are very fragile. Tiny data change, and will see huge coefficient swing. Now let's apply this to a realistic data. Uh, this data can be said very similar to actual Guwahati's temperature data, 365 days of daily mean temperature with seasonal pattern plus noise, similar to the data that was shown in the tutorial. I fit both bases with the polynomial degree 8. Both curves track the seasonal trend beautifully. The RMSE values are nearly identical, but as we have seen, behind the scenes, the Wandermond system is numerically unreliable at this degree, while the Legendre system is stable. This is exactly the motivation from the tutorial. For real data on long time horizons, you want to have Legendre. Uh, Finally, let's have a quick look at the model selection. The three panels that I'm having show degree 1, 5, and 20 using Legendre bases. Degree 1 clearly underfits the data, misses all the curvature. Degree 5 captures the signal cleanly, we can say. Degree 20 chases the noise. It memorizes the training data but would generalize poorly. Both bases show the same bias to variance trade-off. Cross validation or train test split is needed to pick the right degree regardless of whichever basis you use. So now let me summarize what this demonstration showed. First, basis functions. Monomial columns look increasingly alike and Legendre columns stay distinct. Second, condition number. Wandermond grows exponentially, Legendre stays moderate. Third, instability. The same tiny noise causes 1,000 times larger coefficient shift in Wandermond. Fourth, and this is the key insight from tutorial, both bases fit the same curve, same polynomial, and produce the same result. The difference is purely numerical. If you are fitting If you are fitting basically polynomials of degree 5 or higher, or working with real data, always use an orthogonal basis like Legendre. It is simply more reliable, we can say. That was it. Thank you so much for watching this. Here is the summary that I have told exactly the same. Thank you.